All right, let's jump right into this explainer. Today, we're going to explore the absolutely fascinating biological and mechanical universe hidden inside the very clothes you wear every single day. We often take our garments completely for granted, right? Just tossing a shirt on in the morning without a second thought. But today, we are unpacking the incredible science, the complex chemistry, and the honestly grueling agricultural journey that makes natural textiles possible. I want you to take a second and literally look down at the shirt or pants you're wearing right now. Go ahead, feel the fabric. To your eyes and hands, it feels like a solid, cohesive piece of material. But by the end of our journey today, you're going to realize that what you are wearing is actually a highly engineered matrix of microscopic natural polymers. You're essentially wearing millions of tiny, interconnected biological structures. So the crucial starting point is understanding what actually qualifies as a fiber in the first place. You can't just take any random stringy thing and weave it into a shirt. For a substance to be a true textile fiber, it has to possess a mind-blowing scale, a length that is at least 500 times longer than its microscopic width. It's called the slenderness ratio. To put that into perspective, imagine a cylinder that's just 1 inch wide. To be considered a fiber, it would have to be over 40 feet long. This extreme length, combined with flexibility and strength, is exactly what allows these tiny elements to handle the bending and friction forces required to be spun into yarn.
And to really understand the stakes of this whole industry, before we zoom all the way down to the invisible level, consider this massive number. Global cotton production alone accounts for a staggering 26.9 million tons annually. We are literally cultivating almost 27 million tons of microscopic plant hairs every single year just to keep the world clothed. It's an absolutely colossal agricultural undertaking.
Okay, let's zoom all the way into the micro level. When we look at a single fiber under an electron microscope, we see an incredible invisible architecture. A single fiber is actually composed of many smaller fibrillar bundles, and each one of those fibrils is built from thousands of polymer chains running right alongside each other. Think of it kind of like the massive steel cables holding up a suspension bridge. Those giant cables are made of smaller bundles of wire, which are in turn made of even thinner steel threads. Nature engineered this exact same load-bearing structure millions of years ago.
Now, inside those tiny bundles, the molecular chains arrange themselves in two distinct ways. And honestly, this is where the magic happens. On one hand, you have crystalline regions, where the polymers are perfectly parallel, tightly packed, and incredibly strong. On the other hand, you have amorphous regions, where the chains are tangled, loose, and totally disordered. This exact structural balance is what gives your clothes both their rugged durability and their comfortable stretch. If a fiber was entirely crystalline, your shirt would be as stiff as a board. But if it was entirely amorphous, it would just stretch out and fall apart the very first time you wore it.
And you know what? This actually solves a totally everyday mystery. Why your cotton towel absorbs water so incredibly well after a morning shower. It's all about the chemical structure of cellulose. There are these polar OH groups hanging off the molecular chain, and water is naturally attracted to those. They act literally like microscopic magnets for water molecules. So when you dry off, the water effortlessly glides into the porous amorphous regions of the cotton fiber and locks right onto those OH groups, pulling the moisture straight off your skin. So stepping back from the chemistry and looking at the biology, we can see how this all builds up in nature. Cotton doesn't just magically appear out of nowhere, it's the product of the Gossypium plant. What starts out as a delicate, beautiful flower eventually drops its petals to reveal a small seed pod. And over the course of several weeks, the fibers grow inside this completely sealed pod until it finally bursts open into the fluffy, fibrous fruit capsule we all recognize as a cotton boll.
Prepare to have your mind blown here. Every single one of those thousands of fluffy hairs bursting out of that seed, it's actually just one microscopic, elongated plant cell. It's a single, flattened, cellular tube. And if we could slice it open, we'd see incredibly complex concentric architectural layers, a primary wall on the outside, a thick secondary wall made of those highly ordered cellulose fibrils we talked about, and a hollow inner canal called the lumen, which is what used to carry the liquid nutrients back when the plant was alive.
Now when that cotton ball bursts open and gets exposed to the sun, the cell dies and the liquid inside that lumen completely dries up. As it dries, the whole cylindrical cell collapses in on itself into a twisted kidney bean shape. We call these twists convolutions, and there can be up to 300 of these twists per inch. This natural accident of biology is a total game changer. Why? Because these twists create vital friction. Without these microscopic twists, the fibers would just slip right past one another and we would never be able to spin these tiny plant hairs into strong, continuous yarn. All right, zooming back out to the industrial scale, the journey of that tiny dried cell kicks into high gear. First comes harvesting, which is done either carefully by hand or massively by machine. Next is the absolutely crucial ginning phase, where the cotton fibers, which are known as lint, have to be violently torn away from the seeds they literally grew attached to. Finally, the lint goes through heavy-duty baling, where it's compressed into dense 500-pound blocks that are ready to be shipped all over the world.
During this ginning phase, the textile industry has a big choice to make, relying on a really delicate balance. They basically have two main methods. Roller ginning is a slower, gentler process used to preserve delicate, high-quality, long staple cottons. Think Egyptian or Pima cotton. It pinches and pulls the fibers safely. But for your everyday, short staple cotton, they use saw ginning. This is a much faster, high-capacity process that uses aggressive, high-speed cutting discs. It's fantastic for mass production. But the catch is, it literally cuts and breaks some of the fibers in the process.
But here's the wild part. Even after all that intense industrial harvesting and ginning, raw cotton lint is still far from pristine. It actually contains up to 8% of what the industry casually calls trash content. That means a brand new, heavy bale of factory cotton is secretly full of dirt, broken seed coats, leaf and stem fragments, and even mineral dust and sand blown in from the fields. It is a very messy, raw agricultural product at this stage.
Section 1. Grading and testing fibers, the science of quality control. Before any of this messy raw material even gets close to a loom, it has to pass a pretty intense gauntlet of quality control. Modern textile engineers absolutely do not guess when it comes to quality. They aren't just running their hands over a bale to see if it feels soft. No, they use cutting-edge, state-of-the-art tools. They use high-volume instruments to measure strength and fineness. They use X-ray diffraction systems to look deep inside the fiber to measure those exact crystalline and amorphous structures we discussed earlier. They even use UV spectroscopies to check the chemical composition. This is literally high-level physics and chemistry applied directly to a plant.
Using all that incredibly precise data, they rigorously grade the fibers based on things like length, uniformity, and color. But get this, they also grade based on maturity. Depending on the weather and the overall health of the plant, some fibers never fully develop their thick secondary cellulose walls. The industry literally classifies these as dead fibers. And dead fibers are bad news. They're weak, they don't absorb dye properly, and they can completely ruin the look of a final garment. So quality control ensures those dead fibers are strictly weeded out.
Section 2. Jute, the golden fiber of the East.
Okay, let's shift gears completely. We're moving away from the fluffy seed hairs of cotton and looking at a totally different plant, jute. Cultivated heavily in the rich, humid tidal basins of Bangladesh and India, jute is what's known as a bast fiber. It doesn't grow inside a delicate flower pod. Instead, it's extracted directly from the outer skin, or the bast, of the towering stems of the Corchorus plant, which can grow up to 10 feet tall in that hot, wet climate.
Turning these giant woody stalks into a workable fiber is honestly an incredibly labor-intensive process. After the tall plants are harvested, they go through a process called retting. Farmers submerge entire bundles of the stalks in slow-moving water for weeks, allowing bacteria to naturally rot away the sticky cellular glues that hold the plant together. Only after this rotting process is complete can the farmers stand in the water and manually strip the long golden fibers away from the inner woody core entirely by hand. For the longest time, jute was really just used for cheap burlap sacks and ropes. But as global industries are desperately searching for sustainable solutions right now, this quote beautifully captures why this ancient biodegradable fiber is experiencing a massive modern renaissance. It's got high tensile strength, it breathes, and unlike synthetic polyester fibers that are derived from petroleum, jute breaks down harmlessly right back into the earth. It is an incredibly eco-friendly alternative to plastics that naturally protects our environmental balance.
So what does this all mean for us? Well, the next time you throw on a comfortable t-shirt or carry your groceries in a sturdy burlap tote bag, I really hope you'll take a moment to actually feel the fabric. Think about those polar molecules pulling away moisture, the thousands of microscopic twists creating friction, and the rigorous agricultural labor woven into every single thread. Knowing about this invisible universe hiding in plain sight, how differently will you look at your own wardrobe tomorrow? Thanks for exploring this with me, and keep questioning the world around you.